Good afternoon, everyone. I hope you're all fine and I hope you're all safe and healthy. I really miss our classroom meetings and I hope all this shall pass soon. Remember our last topic was finding solutions for systems of linear equations, and we considered 4 different methods for finding solution of systems of linear equations. Now we'll move on to a different topic called functions. I'm sure you're all familiar with functions and you've dealt with functions before at some point of your mathematics study, let's say. But we'll shed more light on what is a function, the definition of the function, and some of the concepts related to functions. And then we'll see how can we use these concepts in solving applied problems, applied practical economic problems. Before we define a function, we will first introduce a mathematical relation, and we'll see shortly why. A mathematical relation is usually expressed in the form of the ordered pair x, y. And we say that a mathematical relation in x and y is given by the ordered pair x, y. In what sense? In the sense that the first component in the ordered pair is the input to this relation, and the second component of the ordered pair is the output of this relation. So a mathematical relation takes an input value x, apply a certain rule, and give me an output value y. Okay, so this means that the order is important. The order in which the values appear in the ordered pair, as the name implies ordered pair, is important. So whenever I'm giving you an ordered pair like this, and this ordered pair represents a mathematical relation or simply a relation, then this means that the first component of the ordered pair is the input to this relation, and the second component is the output of the relation after we apply the rule of this relation. In order to be able to just understand what's a relation, let's take this example. Assume we have a relation in terms of the area of the square given by these ordered pairs, in which, as we said, the first element is the input of the function, of the relation, and the second element is the output of the relation. So this means the first element, if you give me a square of side length 2, then this relation will give you an output of an area equals to 4. How does this happen? The area of the square, as you know, is the side multiplied by the side, or the length multiplied by the length. So it's the length squared. So if you square the 2, this will give you the 4. This is a relation in which we have an input and the corresponding output. Similarly, here, if the side length is 4, the corresponding area would be 16. So this is our x and this is our y. Similarly, if the side length is 3, then the area would be 9. If the side length is 7, the area would be 49. So it's as if our relation is based on an input, which is the side length, and then a rule, which is the area, which is the square of the side length, to give me the output, which is given as the second component of the ordered pair. We said we're mainly interested in functions and not in relations, but in order to be able to define a function, we need first to define a relation. Why? Because a function is a special case of a relation. In what sense? If we have a relation between x and y, we can say that this relation is a function only under one condition. If for every element in the input set x, there corresponds exactly one element in the output set y. That is, each element, each input element, each x corresponds to only one y. If your x, the input value, corresponds to more than one output value, this means that this is not a function, it's only a relation. That's why we say any function is a relation by definition. But not all relations are functions. Why? Because in relations we didn't specify this condition. We just have a set of input values, a set of output values, and a rule that takes me from the input to the output values. but especially with functions, there is a rule which says for every element in the set of x, there corresponds exactly one element in the set of y, which means that each input corresponds to only one output value. If this is satisfied, then your relation is a function. If this is not satisfied, then your relation is not a function, it's just only a relation. So in other words, a function is a rule, a relation, which operates on an input value, which we call x, to give me one and only one, and this is the condition, the very important condition, output value. So we still have a relation, we still have an input and an output, but the important condition is that the input, each input corresponds to one and only one output. So this means that we have a function and not a relation. For example, again, we'll go back to the area of the square example. The area of the square is in fact not only a relation, but also a function. Why? Because for every side length, there corresponds only value for the area y. So each input value corresponds to only one output value. And this means that our relation is also a function. This diagram can be helpful for showing the importance of the condition that is applied on a relation to be a function. We have an input value x here that goes into a machine or a rule, which is called the function, the f function, and we have one output value which we call usually y or f of x. So again, I take each input value x, and when I take this x and give it to this machine or to this rule or to this function f, it will give me only one output value, f of x, or sometimes we call it y and sometimes we call it f of x. Both mean the output value. In order to be able to let you visualize what do I mean by a function and a relation, and how can a relation be a function and how can a relation be only a relation and not a function, let's take these examples. I'll show you a set of input and output values, and we'll see which of them satisfy the condition of a function and which do not. For example, this one. Assume here we have an input value, an input set, let's say x1, x2, x3, x4. We have four different inputs, and we also have four outputs, y1, y2, and y3, and y4. So we have an input set and an output set. This means that this is a relation, because this satisfies the simple definition of a relation, which is you have input values, and for each input value you have a corresponding output value. Okay, so this is a relation, but is this a function or not? Let's go back to the definition of the function. The function is defined as a relation for which each input value corresponds to one and only one output value. Let's go to each input value and see if it corresponds to only one output value or not. Here x1 corresponds to y1, which is only one output value. x2 corresponds to only one output value, which is y2. x3 also corresponds to only one output value, which is y3. x4 corresponds to only one output value, which is y4. So yes, this is a function. These are examples for a relation of this form. If you said y equals 3x plus 10 or f of x equals 3x plus 10, both are the same. Y and f of x are similar. A function of this form or a relation of this form is in fact a function. Why? Because for each x value here, you will get one output value, y or f of x here. So yes, if you have this form of input set and an output set, this relation is a function. Why? Because each input value here corresponds to only one output value here. Okay, let's move on to another example. Assume we have this input set and this output set. So So because we have an input set and an output set, and we have a relation between each input and each output, so yes, this is a relation, because we said that a relation is just a set of ordered pairs, or an input set and an output set. So yes, this is a relation. Okay, let's move on to the second level, whether this relation satisfies the condition of a function or not. Okay, what's the condition of a function again? A function is a relation in which each element in the input set here corresponds to only one element in the output set here. Okay, let's go to each input and see whether it satisfies this condition or not. Here x1 corresponds to only one value in the output, which is y1. x2 again corresponds to only one output value, which is y2. x3 corresponds to the same value y2 like x2. Does this cause any problem? No, it does not. We said that each input here corresponds to only one output here. It doesn't have to be a different output. So x2 corresponds to y2 and x3 also corresponds to y2, but this doesn't make any problem with the definition or with the condition of a function. Why? Because still x2 corresponds to only one output, which is y2, and x3 corresponds to only one output, which is y2, but they are the same. Both x2 and x3 corresponds to the same output. This is not the problem. This is not violating the condition of a function. The condition says each element here corresponds to only one element here, but it doesn't have to be different. So I specifically use this example to show you that maybe two different input values corresponds to the same output value, but still this is a function. Why? Because each element of x1, x2, x3, and x4 corresponds to only one element of the output set y1 and y2 and y3. Although these two, x2 and x3, corresponds to the same element, but this makes no problem. There is no problem with having the same input values corresponding to the same different input values corresponding to the same output value, because the definition again is that each element here goes to only one element here, but it doesn't have to be different. As long as x3 goes to one element, and x2 goes to one element, and x1 goes to one element, and x4 goes to one element, it's okay, even if these two values corresponds to the same output value. So yes, this is a function. An example of this is the function y equals x squared plus 5. Okay, assume here that x2 is equal to 1 and x3 is equal to -1. Okay, if you substituted 1 here, this will give you 1 plus 5, which is y equals 6. So x2 will go to 6, which is x2, which takes the value 1, will go to 6. Now go to x3. If x3 is equal to -1 and you substituted -1 here, this will be -1 squared. So it will be 1 again. 1 plus 5 is equal to 6. So y will also be equal to 6, although here x2 was equal to 1 and x3 was equal to -1. So it makes no problem that both values x2 and x3 corresponds to the same output value y2. What causes the problem is the next example here. Here let's see if this relation, the relation between these input values and these output values, is a function or not. Again, what is the condition of a function? The condition is that each element in the input set corresponds to only one element in the output set. So let's take the input values one by one. x1 here corresponds to only one output value, which is y1. x2 here corresponds to only one output value, which is y2. But x3 here corresponds to two output values, y3 and y4. This violates the condition, and this is not a function. As soon as I see this one input corresponding to two different outputs, then for sure this is not a function, because the condition says for a relation to be a function, then each input element should correspond to only one output element, and here x3 corresponds to two output elements, which is y3 and y4. So no, whenever you have if it's only one input which corresponds to more than one output, so this is not a function. I hope you can see the difference between this example and the third example. In the second example, we had two different inputs going to the same output. This makes no problem, because as long as x2 is going to correspond to y2 only and x3 corresponds to y2 only, even if it's the same value, but still each input element here corresponds to only one element in the output. On the other hand, here we have the same input value corresponding to two different elements in the output set. So this violates the condition of a function, and that's why we say this is not a function. An example on this might be y equals positive or negative the square root of x. So the same value of x corresponds to two different values of y. For example, if x is equal to 4, the square root of 4 is 2. So y would be equal to positive and negative 2. So the same x value, which is 4, corresponds to two possible values for y, which is positive and negative 2, which means that this violates the condition of a function, again, which is that each input value here has to correspond to one and only one output value here, and this is not the case with the x3, which corresponds to two values, y3 and y4. So now we've seen how to identify a function based upon the set of inputs and the set of outputs, and we've said that if each input corresponds to only one and only one output, then this is a function, otherwise it's only a relation. Now, what if we're given, instead of the set of inputs and the set of outputs, we're given a graph that represents the relation between x and y, and we need to use this graph to know whether this relation is a function or not. We can do this using what we call the vertical line test. The vertical line test is a graphical tool that can be used to check graphically whether a given relation is a function or not. And this is what we call a vertical line. It's a line that is parallel to the y-axis. The vertical line test says that a graph represents a function if and only if every vertical line of this form here that is drawn to the graph intersects this graph at most once. That is, it either intersects the graph at only one point or it does not intersect the graph at all. Again, the vertical line test says that if you're given a given graph and you want to know whether it represents a function or not, you should draw any possible vertical line that you can draw. And if any of these lines intersects the graph, this should happen at most once. This means that if you draw different vertical lines to the graph, either these lines intersect the graph at only one point or they do not intersect the graph at all. On the other hand, if any vertical line intersects or passes through 2 points or more than 2 points of this graph, then this graph does not represent a function. So if you draw any vertical line to the graph and it happens to intersect this graph at 2 points or more, then we say that no, this graph does not represent a function. Let's see this using the next examples. Here we have different graphs. They represent relations between x and y, as we can see here. And we need to know graphically, using what we call the vertical line test, whether these relations are functions or not. Let's start with this first one. What does the vertical line test say? It says draw any or all the possible vertical lines that you can draw. If any vertical line intersects this graph, it should and it must intersect the graph at only one point. it may not intersect the graph at all. But if the vertical line intersects this function here, this quadratic function here, more than once, which means it intersects this graph at 2 or more points, then we can easily say that no, this does not represent a function. Let's try. For example, this is a vertical line. If I draw this vertical line, I can see that it only intersects this curve here only once at this point. Let's draw another vertical line. Again, this vertical line intersects the graph at only one point. So how do I choose the position for drawing the vertical line? There is no rule. You can draw any vertical line at any position and then decide whether it intersects the graph at only one point or it does not intersect the graph at all. In this case, you have a function. But if you can't find a vertical line that intersects the graph at 2 points or more, then you can say that no, this is not a function. Here I've chosen these two and they both intersect the graph at only 1 point. What about this one? If I draw this vertical line, it will not intersect the graph at all. So, in other words, I cannot find the line here, vertical line, that I can draw at any point on this curve and that intersects the graph at 2 points or more. If I cannot find this line, if I cannot find the line that intersects this curve at 2 points or more, then I can say yes, this is a function. Okay, this is what the vertical line tests help us with. Okay, what about this one? If I draw this line already intersects the relation here, the circle, at 2 points, this point and this point. So once this happens, I can easily say yes, this is not a function because I can find different vertical lines, not only one, but one is enough, by the way. I can find the vertical lines that can intersect the graph at 2 points. We said 2 points or more. Here they can intersect the graph at 2 points, here and here. So this violates the condition of the vertical line test for a function. So we can say that this graph represents a relation and not a function. What about this one here? Again, I will try to plot different vertical lines. And if I can find a vertical line that can intersect the graph at 2 points or more, I would say this is not a function. If I cannot find such a vertical line and all the lines I draw either not intersect the graph at all or they intersect the graph at only 1 point, then the condition for the vertical line test for a function is validated and I can say that this graph represents a function. Let's try. Here, this is a vertical line that intersects the graph at only 1 point. What about this vertical line? Again, it intersects the graph at only 1 point. So I can say that yes, this is a function because whenever I draw any vertical line, it will only intersect the graph at 1 point or it will not intersect the graph at all. But I cannot find a vertical line that can intersect this graph at 2 points or more. And hence, the condition for the vertical line test is satisfied and this graph represents a function. What about this one? Here, from the first vertical line, I chose to plot it here because I can say in advance, because of this curvature here, I can find a vertical line that is parallel to the y-axis that can intersect the graph at 2 points, here and here. So, right away I can say no, this is not a function because I can find a vertical line that can intersect either this one, or there are lots of other vertical lines, but only one is enough. I can find a vertical line that can intersect this graph at 2 points, here and here. So the condition for the vertical line test is violated and this graph represents a relation but not a function. Now let's move on to another definition related to functions. We've already considered the definition, but we didn't say the name. What is the domain of the function? And I'm sure most of you are familiar with the notion of the domain. The domain represents the set of all possible input values, x. The x, our inputs, all the possible values for this input set are called the domain. So the domain is the input set, or the possible values that represents the input x. On the other hand, the range represents the set of all the possible output values, or what we call y. So whenever you're asked for the domain of a certain function, you should go and see what are the possible values that x can take, that the input can take. On the other hand, if you're asked to find a range for a given function, then you go and search what are the possible values that y or f of x can take. We said that f of x and y can be used interchangeably in this topic. If I say y equals something or f of x equals something, they are both the same. So to find, we need to find the set of all possible values that y can take. Let's see how can we do this graphically, and then let's see how we can do this even if you're not given the graph for the function. If we need to identify the domain and the range graphically, we can use an easy tip. To find the domain, we move horizontally on the x-axis and check what are the possible values, what are all the possible values that x can take. So we move horizontally on the x-axis. On the other hand, to determine the range graphically, we move vertically on the y-axis and see what are all the possible values that y can take, as we'll see in the next examples. So again, the domain is related to x, so we move horizontally on the graph to see on the x-axis what are the possible values that x can take. The range, on the other hand, is related to y, so we move vertically on the y-axis and see what are all the possible values that y can take. Our first example is given by this function, and these arrows here are very important. They mean that the graph extends upward on the left and extends upward on the right. So it's just a notation, that our indication that this graph continues up till infinity here and here. In order to find the domain, we need to go to the x-axis and check whether each value on the x-axis has a corresponding value on the graph, and thus it can be an input for this function or not. For example, here -3, if you consider it moving upward, we can find the corresponding value for -3, although it doesn't appear on this part of the graph, but I know that this extends upward, so I can find the corresponding value for -3, for example here. Moving on to the right, -2 also has a corresponding value on the curve, -1 has a corresponding value on the curve, and by having a corresponding value, this means that it can be an input to this function. So it can be part of its domain. 0 has a corresponding value on the curve, 1 has a corresponding value on the curve, and so on until 3. 3 also has a corresponding value on the graph if you extended the graph upward. So all the possible values on the x-axis have corresponding values on the curve, which means that our domain is the whole real number R. Now moving on to the range. The range is determined according to the y-axis. So here, for example, 5, now we'll look left and right. 5 has a corresponding value on the curve, which is either here or here. 4 have corresponding values on the curve, and so on until we reach 1. It has a corresponding value, which is 0. But any value that is less than 1 doesn't have a corresponding value on the left or on the right, which means it cannot be an output value for this function. So our range starts from 1 and goes up until infinity, because as we said, this graph extends up here and up here. But before 1, there is no values on the y-axis, which corresponds to a value on the curve. Accordingly, we say that our domain is R, or the whole real number, and the whole set of real numbers, and the range, which is the values of the y-axis on the y-axis corresponding to any value on the curve, goes only from 1 to infinity. And by this closed interval, we mean that 1 is included in the range, and by this open interval, we mean that infinity, which as we know is not a number, is we mean this is only a notation to tell us that infinity, which is the maximum value that the range can take, is open and it is not limited. Okay, so we usually use the open bracket with infinity and negative infinity, and we can use an open bracket or a closed bracket like this one, an open interval or closed interval, according to whether 1 is included in our range or not. Because 1 is included here, we included the range goes from 1 here up till infinity. Our second example here is for a function that is limited between negative 2 and 2, doesn't extend like the previous function. There is no arrow here and there is no arrow here. And you may notice that we have t here instead of x and z here instead of y, but this is just a notation, doesn't make any difference. So the function is equal to z equals the square root of 4 minus t squared, which is exactly the same as saying y equals the square root of 4 minus x squared. Okay, so to find the domain, we go to the horizontal axis here and check whether all the values are included in the domain or not. Okay, as you can see here, negative 3 doesn't correspond to any value on the graph, whether upward or downward. So negative 3 is not included in the domain, and any value before negative 3. Until we reach negative 2, we can find the corresponding value for negative 2, which is 0. And moving onward, we can find that all these values correspond to some value on the graph. For example, negative 1 corresponds to this value, negative half corresponds to this value, 0 corresponds to this value, half corresponds to this value, and so on until we reach 2, which corresponds to 0. But any value after 2 doesn't correspond to any value on the curve. For example, here 2.5 doesn't correspond to any value upward or downward. The same for 3, the same for 4, and so on. So this is an example in which the domain is not the whole real line, the whole real number. No, instead the domain only goes from this value, which is negative 2, to this value, which is 2. These are all the possible values that x can take, or t here can take, on the x-axis. That's why we said the domain is a closed interval from negative 2 to 2, and this bracket means that negative 2 is included in the domain, and this closed bracket also means that the 2 is included in the domain, and any value between them. So we say that the domain is the closed interval negative 2 and 2. Now to find the range, we'll do the same thing but on the vertical axis. As you can see here, on the negative part on the vertical axis, there are no values to the left or to the right on the curve. So this means that our range starts from 0 here, because 0 corresponds to negative 2 and 2. And moving onward, half corresponds to this value and this value. 1 corresponds to a value here and a value here, until we reach 2 here, which corresponds to the value 0 again. But any other value greater than 2, for example 2.5, 3, and so on, will not find any value, will not be able to find any value that corresponds to 2.5 or 3 or 4, whether on the left or on the right on the graph. That's why we say that our range is only the values from 0 up till 2. And how did I know that this value is 2? Because this one is 3 and this one is 1, so what's in the middle would be 2. Again, the domain will be from negative 2 to 2 closed. We say that the intervals are closed here because the negative 2 and the 2 are included in the domain. And accordingly, and also the range moves from 0 to 2 here, and both are closed because the 0 is included in the range and the 2 is included in the range. Any value that is greater than 2 or less than 0 will not be included in our range, because we cannot find any corresponding value on the left or on the right that lies on the curve or the graph of this function. Another example is given by this function. This function is different than the other functions, where we can see that the function is split, or the graph is split into two curves. One on the negative part of the x-axis up till just before 1, and the other part is after 1 moving to infinity. Okay, and again we're using here the notations or the symbols or the variables u and w instead of x and y, but the idea is still the same. We need to get the domain, so we'll go to the x-axis and see if there are any restrictions on any of the values of the real line, or in other words, if some of these values cannot be inputs to this function or not. How can you do this? We just go to the x-axis, we move here to the right and check, does this value has a corresponding value on the curve? Yes, it has a corresponding value here. This value, it has a corresponding value here, and so on. So whenever we're moving to the right, the values have a corresponding value on the curve until we reach just before 1. As you can see here, this line will go down but will never reach 1, will never touch this vertical line. Okay, so to find the value of 1, we might think to go upward, but when we go upward as well, this curve, when it extends, it will just move like this upward without reaching or without touching this vertical line. And this means that 1 doesn't have a corresponding value, whether on this curve or that curve. Moving after 1, all the values have corresponding values on the curve. 2 has a value, 3 has a value, 4 has a value, and so on. So all the values on the real line have corresponding values on the curves, on either this one or that one, except the value 1. Because if we move downward, we will never find the corresponding value for 1, because this curve extends just before 1, and if you move upward, we will also never find the corresponding value for 1, because this curve will extend upward, but like this, like straight, without touching this vertical asymptote, this line. This line is called the vertical asymptote. Okay, why is this? Look at the function. The function says y, or w here, equals 1 minus x, or u here, minus 1, right? Try to substitute u or x equal to 1. You will get 1 over 1 minus 1, which is 1 over 0. And because we can never divide by 0, because this will give us infinity, and infinity is not a value, the 1 is not an input for this function. It's not considered an input for the function with u minus 1 in the denominator, because 1 minus 1 is 0, and this means that we are dividing by 0, and this is not possible. Okay, so the domain will be r, difference. This symbol denotes the difference sign, without or remove from r the 1. And here the 1 is put between braces and not like the brackets of the interval, because it's a set that consists of only one element. Okay, let's move on to the range. We'll do the same thing, but now we're moving vertically. Starting from -3 and any value behind, less than -3. If you moved to the left or to the right, we'll find here a value corresponding to -3, a value on the curve corresponding to -2, a value corresponding to -1, which is 0, a value corresponding to -half, for instance, which is this value, and so on until we reach 0. 0 itself doesn't have a value, a corresponding value on this curve, because like this curve and this part with the x-axis, the same thing happened here with the y-axis. And you can see this also from the function. If you cross multiply these two values, you will get 1 over w equals u minus 1, right? So you can never divide by w for any we can never divide by 0. If w is equal to 0, you can never divide by 0. That's why w, which is our y in this example, can never take the value 0. So you will find that 0 has no value, has no corresponding value. The value 0 here has no corresponding value, whether on the left or on the right, because this curve will extend up till infinity or -infinity, yes, but without touching the x-axis. And here also it will extend to infinity, but without touching the x-axis. So 0 can never be an output for this function. That's why all the values on the y-axis or all the values on the real line here can be viable values for the range except the 0. So the range is equal to r difference or except 0. That's why we'll find an open circle here and an open circle here, denoting that 1 can never be in this domain, in the domain of this function, and 0 here corresponding to this value can never be a value in the range or an output value for this function. Our next example is given by this graph, where this function is different than the functions in the previous examples, in the sense that there is no arrow here and there is no arrow here, which means that the function does not extend upward here and does not extend upward here. The function is restricted or limited to this area and this area. Accordingly, to check the domain of this function, we will move from the left here. Any value before -6 here doesn't have a corresponding value on the curve. Once we reach -6, -6 has a corresponding value here, which is -2. And moving onward, -5 has a corresponding value, -5.5, 4, -4, -3, and so on. All these values, -2, 0 has a value on the curve, and this continues until we reach 5. Any value that is greater than 5 doesn't have a corresponding value on the curve, whether upward or downward. And accordingly, we can say that the domain of this function is the interval -6 closed and 5 closed. And here we say closed with this closed bracket here and closed bracket here, because the -6 is included in our domain and the 5 is also included in the domain. If otherwise -6 and 5 were excluded, for example, you will find on the graph here an open circle and an open circle, because you're not given the function, you're only given the graph. So if you are to determine the domain from the graph, and if the -6 and the 5 were excluded, instead of this bold circles here, you will have an open circle and an open circle to indicate that -6 and 5 are excluded from our domain. But we don't have this here, so we included them in the closed interval -6 and 5. We'll do the same thing to find the range. We'll move vertically on the y-axis. Moving from down to up, we will find that before -5, no values have corresponding values on the curve, whether on the left or on the right. The first value that has corresponding value on the curve is -5, which is here. And then moving upward, all these values have corresponding values on the curve, so they are part of the range. Moving upward, these also have values here until we reach 5. 5 has the corresponding value 5 here. But any value that is greater than 5 won't have a corresponding value, whether on the left or on the right. And accordingly, we say that the range is the closed interval -5 to 5. So the range extends from -5 here all the way through 5, but it stops at 5. It stops at 5 because any value that is greater than 5 or less than -5 will not be presented by a corresponding value on the curve. Okay, now what if we don't have the graph and for some reason we are not willing to plot it? Okay, or you're not asked to plot it, but you're only asked to find the domain and the range for this function. This function is a linear function. It's an equation of a straight line. For those of you who know, this is the intercept and the 3 is the slope, so this is an equation of a straight line. Okay, in case you don't know, don't bother, but we're still finding the domain and the range. Okay, how do we find the domain? We check for any restrictions that might be put on the x values. Is there, for example, a square root? Is there a division like the previous example? Are there any restrictions here on the x values that need to be removed from the real values? The answer is no. X can take any negative value, any positive value. X can be equal to 0 without any restrictions. That's why we say that the domain is equal to the whole real numbers R. Similarly, Y also has no restrictions. Y can take a positive, negative, or 0 value according to the value of x. And there are no square roots, there is no squaring, there is no, for example, division, so we have to care for the division by 0. There is no restriction here on the values of y, and accordingly the range is equal to also the whole real values or the real numbers. Okay, and this is the case in general for any straight line. If you don't put any restriction or any range for your straight line, then in general, if I say y equals 3x plus 10 full stop, this means that the domain will be R and the range will be R for any straight line. Okay, if we're given a quadratic function of this form, and we also need to know the domain and the range, we'll start with the values of x. Are there any restrictions on the values of x? Can x take a negative value? Can x be 0? Can x be 1? Yes, to all three. X can take a negative value and still we can get the square of the negative value. X can be equal to 0 and still we can get the square of 0. And x can take any positive value and we can easily get the square of a positive value. And accordingly, the domain is still the whole real numbers. There are no restrictions on the x values, and so all the possible real numbers can be substituted for x, and the domain is the whole real values. Now we'll move on to the range. Can y take a negative value, for instance? Of course not. Why? Because y equals x squared. So squaring any value will never give me a negative quantity. This means that y is not unrestricted. The values of y are not unrestricted. The values of y are restricted to be either 0 or positive because of the squaring here. Thus, we say that the range is the closed interval 0 to infinity. And we said that this open bracket, this is also another way of writing an open bracket, is usually used with the infinity and the negative infinity. As for the 0 here, the bracket is closed because the 0 can be a value in the range. If x is equal to 0, 0 squared will be equal to 0, so y can take the value 0. That's why we closed this bracket. It's a closed bracket and not an open bracket. We can also express this range as R positive union 0. What does this mean? Take all the positive real values and also add with them the 0 as your range. Because as we said here, y can be any non-negative value. It can take the 0 value and it can take any positive value. So these are two alternative ways for expressing the range of the function y equals squared. Our last example is given by the function y equals x, or f of x equals x. This is an equation of a straight line, a very famous straight line called the 45-degree line. And the question asks us to get f of 0 and f of 2 and then determine the domain of the range of f of x. Okay, what is finding f of 0 and f of 2 here? What does it mean? Find f of 0 means simply go to this function and substitute each x with 0 and give me the result for y, or for f of x. This is a very simple function because y is exactly equal to x, so if we did this, we will find that f of 0 is equal to 0, y will be equal to 0, and f of 2, which is obtained by substituting x equals 2 here, will be equal also to 2. In order to determine the domain of the range, we have two options. We either draw this function, we plot it, and determine the domain and the range graphically, or we can just determine the domain from the fact that this is a linear function. Okay, let's do this. We will have here x, when x equals 0, f of x is equal to 0, and when x equals 2, f of x is equal to 2. Okay, now what if we need to plot this line? We'll just go here and take the point 0 and 0 and make a mark here, and then we'll take the point 2 and 2 and make a mark here, and then we connect these 2 points, giving us the straight line. And as you can see from the graph, the domain is given by all the possible values on the real line, because there are no restrictions on the values that x can take, and similarly the range is given by all the values on the real line as well, because there are no restrictions on the values that y can take. And we already said that for any linear function, or any function for which x is raised to the power 1, is the largest power of x, we call this a linear function, and we know in advance that the domain and the range of this unrestricted linear functions will be R and R. Okay, thank you for listening.